Light cannot escape a black hole. Nothing can once it crosses a certain line in space. For decades, no camera on Earth could even prove these objects were real, only their effects on everything nearby. Then an international team pointed a network of telescopes the size of the planet at one, using a method built for something else entirely. What came back rewrote what scientists thought they could ever actually see. The thing even light can't escape. A black hole forms when a massive amount of matter gets packed into an extremely small space, creating gravity so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. This is not a physical wall or surface. It is simply the distance from the center at which the escape speed needed to break free equals the speed of light itself, which is the fastest speed anything in the universe can travel. Most stellar mass black holes form when a massive star runs out of nuclear fuel and collapses under its own weight. A violent process usually captured today by NASA missions such as SWIFT, which watches the sky for the sudden bursts of gamma rays and X-rays these collapses produce. Supermassive black holes, millions or billions of times heavier than our sun, sit at the center of nearly every large galaxy, including our own Milky Way. Nobody fully agrees on how objects that large first formed, whether they grew slowly by swallowing gas and merging with other black holes over billions of years, or whether some formed almost fully sized in the early universe. And that question alone has kept astronomers busy for decades. What everybody does agree on is that once something crosses the event horizon, there is no signal, no light, and no way to send information back out. The size of that boundary depends entirely on mass. A black hole with the mass of the sun would have an event horizon only about 3.7 miles across, while the supermassive black hole at the center of our galaxy has one stretching millions of miles wide. That single, simple fact that nothing which crosses this line can ever report back is exactly why studying the inside of a black hole became one of the hardest problems in all of science, and why the very first real picture of one took over a century of theory to finally produce. The picture nobody thought was possible. Since a black hole itself cannot be seen, scientists spent decades hunting for indirect proof. Instead, tracking stars that orbited something invisible or measuring radiation from gas falling toward one. That changed in April 2019, when the Event Horizon Telescope Project, an international collaboration linking radio dishes across the entire planet into one virtual telescope the size of Earth, released the first ever direct image of a black hole. The target was M87, a supermassive black hole sitting about 55 million light years away, roughly 6.5 billion times heavier than the sun. The image showed a glowing ring of superheated gas surrounding a dark central shadow, exactly the shape predicted by physics equations written more than a century earlier. NASA supported the effort by pointing its own space-based telescopes, including the Chandra X-ray Observatory, at the same target during the same window of time, adding X-ray data that helps scientists understand the hot gas swirling around the black hole and confirm the source was in a historically calm state at the time of the image. Chandra had already been observing that same black hole for roughly 2 decades before the picture was ever taken, building up a long record that gave scientists context nobody had access to in 1960s style astronomy. In 2022, the same international team released a second image, this time of Sagittarius A, the supermassive black hole sitting at the very center of our own Milky Way galaxy, about 27,000 light years from Earth. NASA missions again supplied simultaneous X-ray and infrared observations to help build a fuller picture around that image. Since Sagittarius A behaves very differently from M87, flickering and flaring on short timescales in a way that made it a much harder target to photograph. Both pictures confirmed a shape scientists had predicted for generations. What neither one could do, and what no telescope built by any nation has ever done, is show what actually happens once matter passes that glowing ring and disappears from view for good. What happens to anything that gets too close? Long before anything reaches the event horizon, gravity itself starts tearing it apart. Because a black hole pulls much harder on the near side of an object than the far side, anything drifting too close gets stretched into a long, thin strand, a process astronomers call spaghettification. NASA has directly observed this happening to real stars, not just modeled it in a computer. In one case, studied using data gathered with the help of ground-based survey telescopes and followed up by NASA observatories, a star wandering too close to a black hole roughly 1 million times. The mass of the sun was shredded, and its remains formed a bright glowing disk, an event known as a tidal disruption event. These events can briefly outshine an entire galaxy, and NASA's Hubble Space Telescope has captured several, including one case where a supermassive black hole quietly drifting through space, undetectable by any other means, betrayed its own hidden location by ripping apart a passing star and lighting up in a burst of radiation across X-ray and visible light. Scientists studying these flares have learned they can reveal a black hole's mass, its spin, and even hint at how fast the destroyed star's debris is moving, with some material clocked at speeds above 20 million miles per hour. Researchers have also found that a wall of gas and dust blown outward by the black hole itself can hide the X-ray light from these events for months at a time, which explains why some tidal disruptions show almost no X-rays at all, even though the underlying physics predicts they should be there. That destructive process happens entirely outside the event horizon, in the region telescopes can actually observe, which raises an obvious question about what continues happening to that same matter once it finally crosses the line where no telescope on Earth can follow it. The point where the math stops working. According to Albert Einstein's theory of general relativity, all the matter that falls into a black hole eventually gets crushed down into a single point of infinite density called a singularity, where the normal laws of physics, as scientists currently understand them, stop producing sensible answers. Space and time, as normal equations describe them, essentially break down at that point, meaning the theory itself cannot say what actually exists there, only that our current models run out of road. This is the honest and important part of the story that gets lost in a lot of coverage of black holes. No instrument, no probe, and no piece of light has ever escaped from inside an event horizon to confirm what a singularity truly looks like, because escaping is physically impossible once you cross that boundary. Scientists are not guessing wildly. Their predictions come from equations tested successfully in nearly every other part of physics for over 100 years, including predictions about gravity, orbiting stars, and bending light that have all been confirmed through direct observation. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously, but a full description of the singularity itself would require combining general relativity, which describes gravity on huge scales, with quantum mechanics, which describes matter on the smallest scales, and these two frameworks do not yet fit together cleanly. Some physicists work on a proposed idea called quantum gravity to try to bridge that gap, but no version of it has been confirmed by observation, and that unfinished merger is considered one of the biggest open problems remaining in physics today. The structure NASA found hiding around every black hole, while the deepest interior remains out of reach, NASA has kept making real progress on the region just outside it. In 2024, researchers using data from NASA's Imaging X-ray Polarimetry Explorer, a spacecraft known as IXPE, published new findings on a structure called the corona, a shifting region of superheated plasma that surrounds many black holes and produces much of the X-ray light astronomers use to study them. Before this study, scientists only had theoretical guesses about the corona's shape, unsure whether it formed a sphere above and below the black hole, an atmosphere generated by the surrounding disk, or plasma sitting at the base of the black hole's jets. By measuring the polarization of X-rays, a property that reveals how light waves are oriented, the IXPE team, led by researcher Lenny Sade at NASA's Marshall Space Flight Center, found that the corona tends to stretch out in the same direction as the surrounding accretion disk, rather than forming a compact sphere as some earlier models had suggested. IXPE also studied a newly discovered black hole system called Swift J1727.8, 1613, first spotted during a sudden brightening event in 2023 that briefly made it one of the brightest X-ray sources in the sky. Watching it move through the rise, peak, and fade of that outburst in a way no earlier mission could manage. This gave scientists their first direct look at a structure that had only existed on paper for decades. That kind of steady, incremental progress on the region just outside the event horizon is what makes the deeper mystery, the argument over what ultimately happens to information itself once it falls in, so much harder to simply set aside. The piece of information scientists can't agree on. In the 1970s, physicist Stephen Hawking predicted that black holes are not perfectly permanent traps after all. Using quantum theory, he showed that black holes should slowly emit a faint form of radiation, now called Hawking radiation, and very gradually lose mass over immense stretches of time until they eventually evaporate away completely. No telescope has ever directly detected this radiation, since it would be far too faint to pick out from the background of the universe for any black hole currently known to exist, but the underlying math behind the prediction is widely accepted among physicists. That discovery created a genuine problem. If a black hole eventually evaporates completely, physicists have long assumed that the information about everything that ever fell into it, every particle's exact properties, should not simply vanish from the universe forever, since quantum physics generally treats information as something that cannot be destroyed under any circumstances. Yet Hawking's original calculations suggested that evaporation would erase that information completely, a contradiction now known as the black hole information paradox. Different groups of physicists have proposed different solutions over the decades. Some argue the information leaks back out slowly, hidden inside the pattern of the escaping radiation itself. Others propose that a thin, highly energetic boundary, called a firewall, might sit right at the event horizon, breaking some of general relativity's own assumptions in the process. Progress has been made using advanced quantum modeling and mathematical tools borrowed from string theory. But there is still no single answer that the entire physics community has settled on. And that lingering disagreement connects directly to a much more grounded question about what any of this actually means back here on Earth. What it means for Earth. No known black hole poses any direct threat to our planet. The nearest confirmed black hole to Earth sits roughly 1,560 light years away, an enormous distance that puts it far outside any range where its gravity could meaningfully affect our solar system. Even the supermassive black hole at the center of our own galaxy, despite its enormous mass, is too far away and too gravitationally balanced by the rest of the galaxy to pull anything toward it from where Earth sits. Studying black holes matters for a very different reason. They are the most extreme laboratories for gravity that exist anywhere in the universe. And testing Einstein's equations under those extreme conditions is one of the best ways scientists have to check whether current physics is missing something important about how the universe actually works. Every prediction confirmed near a black hole, from the bending of light to the exact shape of its shadow, adds confidence to a body of physics that also underlies GPS satellites, spacecraft navigation, and basic engineering used every day on Earth. Black holes also help explain how galaxies, including our own, grow and evolve over billions of years, since the supermassive black hole at the center of a galaxy can influence star formation across enormous distances through the energy and radiation it releases. Every new dataset NASA collects, whether from Chandra, IXPE, Hubble, or Swift, adds another piece to a puzzle that connects the most violent objects in the universe to the ordinary physics that shapes stars, planets, and eventually, life itself. What it all adds up to. Nobody has ever seen inside a black hole, and current physics admits the honest limits of what it can predict once matter crosses the event horizon. What NASA and international teams have documented instead is everything happening right up to that boundary. Glowing rings of gas, shredded stars, shifting coronas, and radiation patterns that keep testing the edges of known science. None of this is speculation. The images came from the Event Horizon Telescope in 2019 and 2022. The corona findings came from NASA's IXPE mission in 2024. The tidal disruption events were captured by Hubble, Swift, and ground-based survey telescopes. Every piece came from real instruments and published research, and every open question, from the singularity to the information paradox, remains one of the most active arguments in modern physics today. If this video gave you something, subscribing takes 3 seconds, and it helps us keep making content like this.